Okay, so today we are starting the discussion of types of random processes. Types of, let's say, white sand stationary random processes. Okay. So the first one is number one. This is called moving average process. Moving, let me see, average process. It's also called MA process. So what is the setup that we are interested in? Well, the setup is as follows. Now, W of n is white noise. So this is the input of the filter with variance, let's say sigma W square. Okay. Now, in this case, in the moving average case, H of C is a causal, let me see, FIR, important part is FIR filter. In other words, H of C is, or let me write H of n. H of n is in this form, impulse response of this filter. So let's say that this is H of 0, I have H of 1, I have H of 2, etc. up to, let's say, H of Q, let's say. Okay, something like that. And all zeros afterwards. Okay. So what do we see? This impulse response is causal. So it's 0 also for the negative indices. And it's of finite length. Okay. So this forms the moving average process. So you may wonder why this is called the moving average process, but I think it will be clear. If you check this input-output relationship of this mapping, now X of n is nothing but convolution of the input with this type of an impulse response. Okay? H of n. So how can I write this one? So I can write this as H of k, x n minus k, k from 0 to this one to q. Okay? So I have q plus 1 taps. These are also called taps, especially in communications. Okay? So this is a finite number of taps, and I'm doing the convolution, h of k times x n minus k, this type of a relationship. So if I write this, let's say, for, let's run this summation, h of 0 times x of n, k is equal to 0, plus h of 1 times x n minus 1, goes like this. H of the last one is q times x n minus q. So what do we observe? So we observe the following. If x of n, if w of n is, sorry, this is w of n, this is the input. If the input is, let's say, something like this, it's the sampled version of this. So the output is nothing but, let's say I'm at this point, I am taking the weighted average of last q samples, including this sample in the history. So let's say that last q samples, including, this one. So I have q samples over here. Let me write q plus 1 samples. Okay. So it is nothing but, if this is input w of n, this is w of n, this is wn minus 1, so this indices n minus 2 and so on. So what do I have? If I do this operation, this current sample is multiplied by h0, previous sample is multiplied by h1, so the one before this, second previous, let's say, is multiplied by h2, and the last sample is multiplied by HQ in this window and summed up. Okay? And this process is repeated for all inputs, for all time indices. So if I shift this window towards right, this process is always, this is what we call this convolution. And what we see is, this is nothing but a moving average operation. Because I'm calculating the average of these input samples in a finite window with these weights. Weights are these, the values of this impulse response at different indices. Okay? So this is nothing but weighted sum of a finitely many samples of the input. And this is called a moving average filter. And when I filter this white noise sequence with such a filter, I get this moving average process. Okay? So I think the name is clear. Now what is our task? Our task is understanding if I have such a random process generated by this moving average filter. What are the properties of this random process? In other words, what is the output autocorrelation? Let's say power spectral density, etc. Okay? So I know the following from my earlier analysis. Output power spectral density is nothing but, this is the correlation. Okay, so if this is the autocorrelation of the output, but let's focus on this. This is equal to sigma W square S because of this white noise condition with variances. And power spectral density is, okay, so this is input power spectral density times filters. Let me erase this part. Magnitude response in square. Okay, so I have a DTFT relationship in between these two, and for this case this is nothing but the Fourier transform of this constant sigma W square. Okay, so what I need is to understand this operation, because other than that there is nothing else, and the magnitude response of this filter, this FIR filter. Okay. So let me write some remarks. Number one, moving average filters are all zero filters. Okay, so what does that mean? They do not have any poles other than trivial ones at z is equal to infinity and possibly z is equal to 0 and so on. Okay, so other than those ones. So they do not have any, non-trivial, let's say, poles. Okay, these are all zero filters. Okay, so they don't have any poles, but they have only zeros. So let me, number two, pole zero diagram. So if I sketch this pole zero diagram, maybe, something like this. So it consists of, for such an H of C, so this is my moving average filter. So what do I have? I don't have any poles, but I have only zeros. Let me, mark one of these zeros over here and the other one over there. Okay, to make it impulse response real valued, I need to have complex conjugates of these zero locations also. Okay, so what is the order of this? It has 4, as you see, poles. Okay, so that means that I have a fourth order system, and that means that this is Q is equal to 4 in this case. Okay, that is it. Now these are my, as I have said, zero locations. So what is this one? This is the unit circle as before. J minus 1 minus J. So this is the real part of Z, this is the imaginary part of Z, and so on. Now what I need is, this filters magnitude response. Okay, so it's DTFT. So how do I evaluate this DTFT? Well, you can say that DTFT is nothing but, let me use this. If this is omega, I measure from here, omega. And this point is, Z is equal to e to the j omega. Especially you can see it very immediately, immediately from polar coordinates. Okay, what do I mean by polar coordinates? What is the magnitude of this complex number? It is 1, it's on the unit circle. What's the angle? Angle is omega. Okay, so as Z is equal to j omega, I'm evaluating this h of Z at this point. Okay, Z is equal to j omega. If I change this omega on this unit circle, starting from 0, omega is equal to 0, and if I evaluate it by going around this circle, I get this. Okay, this is what we call filters. Magnitude or phase response can be calculated like that. So let me then write this. If my h of z is something like this, so this is h0 plus h1, this is hq, z minus q. So hq is hq, this sample. Okay, this is another notation, you may say. So as you see, this has, as I have said, q poles. In this example, it has only 4 poles. Okay, so how can I write this? I can write this as k, there is a constant, times, not poles, it has only q zeros, as I have said. Okay, so these are the 0 locations. Zk's are zeros of h of z. Okay, so for example, this can be 0 number 1, this can be 0 number 2, which is equal to 0 number 1 conjugate. Okay, so this is 0 number 3, this is 0 number 4. I have such a case. Okay, now how can I understand this one, h j omega? If I understand this, essentially I get this power spectral density, if I can understand this one. So from this pole zero diagram, there is a way of understanding what is going on in the spectrum, and that is, well, if you check from here, so you can interpret magnitude spectrum or phase spectrum, okay, by looking at this pole zero diagram. So h j omega, if you insert z is equal to j omega, and if you calculate its magnitude, let's say, then you have magnitude of k, am I right, times the magnitude of this. But this is nothing but the magnitude of this, because it's just a product, and instead of z I am writing e to the j omega. Now here is the issue. If I am at this point, okay, in order to calculate this, I need to calculate, there's a constant, such quantities. So what is this? If you think about this one, this is nothing but actually this. Okay, so please interpret this like a vector. So this is this red vector. Okay, zk is this, let's say, green vector. So this is my z1. Okay, so what I see is this is a difference vector. So z1 plus this difference, z1 plus this difference gives me this. Or let me erase this once you are used to these. So this is difference of two vectors. So it is a vector pointing towards z is equal to e to the j omega from this z1 point, isn't it? But this is the magnitude of this, you may say, complex number or vector. Okay? So in this calculation, if I am at this point, this complex number is nothing but the magnitude of this vector. Okay? So this is the magnitude of other vector. And so on. Okay? So in this calculation, if I have 4 vectors, then I'm multiplying these 4 magnitudes and getting a number, and multiplying that number by k and getting the magnitude response in magnitude at that point. So if I move my j omega point to elsewhere, of course these vectors are changing, but I repeat the same calculation. Okay. Now, let's say that, you know, this is at, I'm just making this up, at pi over 4. And this is at 3 pi over 4. Okay, I'm writing the angles. So what happens? How can I roughly sketch this? So 8 j omega magnitude, as you see, I am doing this sketch in 0 to 2 pi, but I think the periodicity is clear, especially from this discussion. Okay. So at 0, what do I have? At 0, I'm at this point, so I'll multiply this length by this length, times this length, times this length. I get a large quantity, something like this. So if I move towards this first 0 location, 0, 1, where was it? At 3 pi over 4. At pi over 4. So you see that, you know, this distance is getting smaller at least. If I move, let's say, towards this, at this location, omega is equal to pi over 4. Then this distance will be small, and one of these factors will be small. The other ones can be large, but, you know, since I'm approaching this 0 location, so I'm expecting this magnitude to decay around this point, okay? And it will further increase at the other point. And there will be at 3 pi over 4, let me write 3 pi over 4 over here. Or let me make this sketch a little better. Okay, this is pi over 4, pi over 2, 3 pi over 4. Let me have at least something like this. Pi and so on. Okay, so this is again increasing, but around 3 pi over 4. So again, I see even since this is closer, at least from this picture, it is closer to this third 0, then the response around 3 pi over 4 is further small. Okay, so again it will be increasing, and it will be repeating this kind of, you know, pi, 5 pi over 4, and so on. Let me sketch at this, up to this. And let me do the sketch the other way around. Minus pi over 4. Okay. So this is minus pi over 4. This is minus 3 pi over 4, and so on. Okay. So this is, as you see, I have something like this. So, of course, if I travel on the first 2 quadrants, and if I travel on the last 2 quadrants, third and the fourth quadrant, I get the same response, because the, you know, the picture repeats itself. The calculations are exactly the same. Okay. So what I see is, well, because of zeros around, let's say, z is equal to e to the j omega, or let me write pi over 4 e to the j 3 pi over 4, we observe valleys like dips, etc., around these frequencies. Okay. So this is the type of behavior that we observe. So if you take the square of this, magnitude square, if you take the square of this, you get the power spectral density. So by just looking at this picture, so you get the magnitude response, and immediately from this magnitude response, you can also sketch the power spectral density of this process. So what we see is the following. Let me erase this part. So, for MA processes, we expect to see dips, let's say valleys, in the power spectral density. Okay, this is one of our conclusions from our knowledge of, this type of pole zero discussions. As you see, pole zero concept is extremely important. Why it's extremely important? To understand such, filters, magnitude response or phase response, because of this kind of interpretation, distance interpretation. So you are always calculating the distance of this, let's say, zero location from a point on the unit circle. Okay, and the magnitude of these vectors in the phase response, angle of these vectors, they are added up or subtracted. Okay, so in the phase response, the magnitude will be, as you see, they are multiplied. So for example, if I have a, this 0, 3 happens to be on the unit circle, then this will be exactly 0 at this point, obviously. Because while traveling on this, I hit a 0, then this makes this, this magnitude response 0. So this is the power of transform domain or pole zeros, because you can also interpret what is going on outside of this unit circle by locating these poles and zeros. Okay, poles and zeros of this filter on the complex plane. So this unit circle, that is DTFT, becomes a very special case, and if we are only focused on DTFT, we cannot understand what is going on clearly because we cannot see these poles or zeros. Very good. Now what is the next topic? Now, so this is an observation. Next, let's try to calculate MA process autocorrelation. Okay, actually it is this. Well, there is not much to think about because we have a general formula. So then Rx of k, if this is an MA process, then this is equal to sigma w square. Convolution of this is giving itself. Oh, this is, sorry for that, h of k, sigma w square, h of k minus k conjugate. Okay. I have, is this all correct? Okay. I have this. So how can I, calculate this one? Let me erase this. Let me keep this. Maybe I can use it later on. Okay. So let me try to save this. Okay. So this discussion, now it goes on over here. Rx MA process K. So sigma W square. So I need to do this convolution. So how can I do that? H of L, or let me put minus L over here. This is with conjugate K minus L. Okay. So this is this, and K minus L is the other one, and dummy variable is L in this convolution. Dummy variable is L. This is my one of these inputs. I have this. So this is the end actually, but let me do some more operations on this because it looks a little different. So let me express this. So instead of L, I will first write minus L. I am doing this a little bit faster because we have done such things before. Now I can do this. I should also change the summation indices, but you know, it will be ranging from infinity to minus infinity, and addition is commutative, assuming that this is finite. Now we are done. That is it. But there is a conjugate also over here. So what should I do next? Well, Rx, this is okay, but it's not in the form that I like. I think you will appreciate it a little better when I am done with this. Okay, I have something like this. Now, let me do this. Let me take the conjugates of this side, and let me write k is equal to, instead of k, is, let me write minus k for k. Okay? So I will do the same thing on the right side also. Okay? Instead of k, I'll write minus k. And if I do this, Rx MA process minus k, well, there's a conjugate, is equal to sigma w square. So what else? L minus infinity to infinity. Now this term is not conjugated anymore. This is the one that is conjugated, and this becomes L minus k. Okay. So instead of k, I'm writing minus k. Because this is valid for all k, I can, you know, do any kind of such substitutions. Then we are done. Okay. So I want this conjugate on the second one, this shifted one. The reason is, from our definition, this is also Rx MA k. Okay. Because autocorrelation sequence for Y-sense stationary processes are Hermitian symmetric. Then I get this, Rx moving average. Okay. The reason I want to have such a thing, because in the classic, you know, let's say in MATLAB packages and textbooks and so on, this is called the deterministic autocorrelation. This calculation. Okay, deterministic autocorrelation. What do I mean by deterministic? As you see, there is nothing random over here. So this is the impulse response to samples of the filter. Samples of the impulse response of the filter is, you know, calculated according to what we call not the convolution but the autocorrelation operation. Okay. Of course, this summation is general, minus infinity to infinity, but this is taking values in 0 to q. So this goes from 0 to q. Okay. Because of this first term. So again, the second term, when L minus k is in between 0 and q, this is non-zero, and so on. Okay, for finite impulse response length, these summations are, you know, this starts from 0 to q, etc. Summations are, but this is the general form which is always valid. Okay. So what do I mean by deterministic autocorrelation? So again, let me try to explain over here. Deterministic autocorrelation. For example, in MATLAB there is a command xcore. If you write xcore h, a vector, this calculates something like this, exactly this one. So what do I mean by that? Well, let's say that my h of, h vector is h of n. Okay. So I have zeros. So I have h0, h1, h2. Let's say q is equal to 2 in this example. Okay, hn is something like this. So this is abuse of notation a little bit, but so this is h of n, but please consider this like an infinite length vector. Okay. So this is the indice when n is equal to 0. So if I sketch this, this will be the sample at the origin. Okay, this is the sample at the first, sampling time, and so on. Since q is equal to 2, I have only, 3 non-zero samples over here. Now in this calculation, I have h n minus 1, shifted version of this. So what do we see? 0, 0, 0, 0, h0, h1, h2. The rest is again all 0. This is again the vector shifted one more time. 0, 0, 0, 0, 0, h1, sorry, h0, h1, h2. It's all 0. Okay. So what's going on? So when k is equal to 0, so in this calculation, let me go over here. So when k is equal to 0, what do I have? So when k is equal to 0, Rx0, sigma w square, and I have, forget about this conjugate for now, let's assume that they're all real valued. In this example, I am taking the squares of, only this. Squares of whatever I have from minus infinity to infinity and summing them up. Okay? Take the square of every element and sum them up. How about k is equal to 1? Now I have h of L, let's say, okay, and this is shifted towards right by 1. Okay, L minus 1. So what do I have? This sequence, this can be L or N, whatever it is. So these two are pointwise multiplied and sum them up. Okay. So h of n is shifted by 1 towards right, shift operation, and multiplied. So I see non-zero terms like this. h0, h1, h1, h2, and so on. Okay, so this is how MATLAB or any other computing facility calculates the deterministic autocorrelation by such an operation. Okay, when k is equal to 2, okay, h of n minus 2, let's say. Okay, this can be L or N, dummy variable. So the original sequence shifted by 2. Okay, pointwise multiplied. Okay, then I get the result. So if I do this, I only get this term, h0 times h2. Okay, how about k is equal to 3? Rx3, this is equal to 0. Okay, is it? This is this, and it's equal to 0. Okay, that is it. So what do I have? I see the following at the end of this calculation. If I sketch this Rx of moving average k, okay, for q is equal to 2, I see, such, let's say, samples. So this is Rx0, Rx1, Rx2, and so on. Okay. And for the negative lags, what can we say? Well, because of the symmetry, Rx minus 1, and the rest is all 0. Rx minus 2, and what we have, zeros everywhere. Okay, that is it. Okay, so this is 0, 1, 2, minus 1, minus 2. So what we have seen that if I know this filter's impulse response, calculation of this, autocorrelation, output autocorrelation, that is the moving average processes autocorrelation, is nothing but this kind of a calculation. Okay? So this is essentially a deterministic autocorrelation result times sigma w squared, that is it. Okay, so the reverse, assume that somebody gives you this autocorrelation sequence, somebody gives you this autocorrelation sequence of a moving average filter, moving average process. Okay, so the question is, can you find the filter? Okay, can you find, you are right now given Rx of k, and can you find these H0, H1, H2 from this? So let me write this. Well, number one, observations. Number one, finding Rx of k given H of n is simply by deterministic autocorrelation. Which is basically nothing but convolution, deterministic autocorrelation for MA process. Number two, finding, let's say H of C filter having a desired Rx moving average K autocorrelation sequence, the reverse problem requires solving nonlinear equations. So what are those equations? For example, let me put star over here, as in star. Okay? So you need to find H0, H1, H2 from these three equations. Okay? That is it. So if you can solve those equations, if there is a solution, you are done. Okay? Now, let me write this. The solution of nonlinear equations is difficult, obviously, not easy, but can be done by spectral factorization. We will explain this later on. Spectral factorization. Let me say, let me put this, but can be done is difficult, is more difficult, let's say, because it's not very difficult, it's more difficult than a linear equation system. It's not trivial, but it's possible to get the solution also. Okay. What else? Now, very good. Now I would like to discuss, this is the end of moving average processes. So as you can see, this is type number one. Now I would like to discuss the second process, and this is number two, auto-regressive processes. And these are called AR processes. Okay? So what is this one? So we have the same setup, but only difference is now h of z is, I have k 1 minus, well, let me look at my notation. This is b0 plus 1 to p number of poles qk z minus k. Okay, so this is my h of c. This is q. So right now this h of c is in this form. So what do we observe? Now this is all pole system. Okay, so there are no zeros there can be trivial zeros at infinities and plus infinities and 0, so on. But other than those trivial zeros, we don't have any zeros in the system. Okay, so it is the complement of this picture. This was all 0. Now I have an all pole system. Okay. Now the question is, if I have such a system, what do I observe? If this system is excited by white noise, what do I observe at the output? What kind of process do I have? Okay. So I will draw the same picture, almost like the same picture. Okay, something like this. Let me put this time poles over here. Again, this has, poles at, let's say, pi over 4 with the, angle 3 pi over 4, let's say. Okay. So this time p is equal to 4. It has 4 poles over here, and this is the pole 0 diagram, real part, imaginary part. Okay. So if I repeat this, the same calculation, what do I have? Let's say that I am at this point. This is z is equal to e to the j omega. Okay. So what do I have? So what am I trying to achieve? I would like to understand a j omega, let's say, magnitude. So instead of z, I'm writing e to the j omega and taking the magnitude. So this magnitude of b0 plus magnitude of am I right? It's something like this. But I know these pole locations this time. Again, let me call this P1. This is pole 1 conjugate, pole 2 conjugate, and so on. Okay. So I can write this also in this form. Let's say that I have a constant over here, k, divided by, this is, I have p poles, z minus pk. This is kth pole. Pk is the kth pole. Over here, zk was the kth zero. Okay. So what do I have? So this e to the j omega. So instead of this, I should write e to the j omega. Okay. So what do I expect? Now this pole location is fixed. 4 of them, they are fixed. And this z on the unit circle, I am traveling. And again, I am calculating these distances. The same distance calculation comes into play. So 4 distances, 1, 2, 3, and 4. Okay. I have 4 distances from each pole. So assume that this is something like an elastic thing, like rubber band. You move this, then these arrows are pointing towards this red point, and they are changing, obviously. So the issue is this: when this distance is small, one of these distances is small, you are dividing by a small number. Okay. So if you divide by a small number, you get a peak. You get a high response at that location. Okay. Then what do I expect? Again, let me try to sketch from minus pi to pi. So let's say that 3 pi over 4 is here. No, this is pi over 4, right? First. Pi over 4, 3 pi over 4 is here. So what do I see? Now this time, at the origin, I am at this omega is equal to 0. I am over here. So I have some distances. But I am dividing by the product of those distances. So if distances are large, then I'm dividing by large number, but as you see, now I'm approaching here, I'm getting a peak, because I'm dividing by some around this, of course. It's not exactly the peak location. And this can be even a higher peak. Okay, it may be something like this. Of course, in the other way, if I travel, this is repeated. Okay, this is not the exact zero, it's small, I guess. Minus 3 pi over 4. This is minus pi over 4, and so on. So is this clear? This red point on the unit circle, you are traveling for every omega, for every angle on the unit circle. Then you calculate these distances from the pole to this red point on the unit circle. And if one of these distances is small, then you are dividing by a large quantity. So what we see is, this is h j omega magnitude square for, let's say, all pole filter. So what we observe is the following. So if omega is, or let me write e to the j omega, e to the j omega is close to pole locations, we observe a peaky response, around, let's say, omega x. Omega is equal to omega x. Okay? If for a particular omega x, this omega x is close to maybe this one of these poles, so we get a peaky response. So what do we observe? So for AR processes, h j omega magnitude square sigma w square, that is power spectral density, is peaky and has some resonance type response, or not response, but has some resonance type shape in the spectrum, or resonance type shape because it's already spectrum. Okay. So this is very different from this moving average processes. Now I see this time not valleys, but I see some peaks in the spectrum. So if you observe things like that, now you can understand that this is more likely to be if you observe, for example, such a, let's say that this is the power spectral density of a process, because of these peaky behavior, you can maybe guess that this is more like an AR process. Okay? Very good. Again, we see the utility of pole zero definitions one more time in this discussion, in the interpretation of this. Okay? So what else? Again, now some issues. Let me try to do this over here. So this is the type of the filter, and this is the general shape of power spectral density, we may say. Okay. Now again, let's try to do autocorrelation calculation. For AR processes. Okay. Again, you may say that, well, we have the general formula, R x of k, now this is AR process output, is equal to, well, I'm just writing it faster, sigma w square, HAR minus k conjugate. Okay? So this is, let me, if you wish for once, let me write AR over here. So this is the AR process's impulse response. Okay? So this is Z inverse of HAR of C. Okay. So this is an infinite length sequence. Okay. So this is infinite length sequence, and so what should I do with that? Maybe that's not a good way of dealing with this. Okay. Okay, so we will be using another method to derive this autocorrelation sequence, but I will write an assumption over here. Number one, assumption. One, we assume that this HARZ corresponds to a causal all-pole filter. Okay, so important point is, now we have introduced this causal discussion, causal all-pole filter. So that means that, again, the impulse response of this, if I sketch this, HARN, it starts from 0. It may take some values. So this is an infinite length sequence, okay? So this goes like this maybe forever, but it's a causal sequence, okay? So this is N, 1, 2, 3, minus 1, minus 2, minus 3. So this corresponds to a causal. This is our assumption. Actually, when you define something in Z domain, for the sake of this calculation, you don't need to have this region of convergence discussions. So only thing that you need to have is, well, the behavior of this function on the unit circle, okay, which you can always calculate. But the issue is whether that will be a meaningful calculation or not depends on whether this unit circle is included in the region of convergence or not, okay? You know, the Z transform discussions. So we will be always considering causal filters because that is the one making sense in the applications. And with this causality assumption, what can I do? Now, this is not a good way of calculating autocorrelation because, you know, I have to calculate this infinite length sequence, shift it, do this multiplication, shift one more time, do this multiplication, and so on, and it's not very insightful. So this will be just like a numerical calculation. So instead of doing so, now let me write the following. H of C, this AR process. This is equal to B0 plus a QK. Is this Q? Let me see. Let me write over here AK. Sorry for this. AK. Okay. B0, I have these. Z to the minus K. Okay. So, what should I say about this one? Again, I also know that this corresponds to a causal H of N. Okay, HAR of N. In other words, infinity is in the region of convergence of this. So can I also write this? This is the transfer function, as we have said. This is x of C divided by this. Okay. So this is the output in Z domain. This is the input in the Z domain, and that is the transfer function. So can we say the following? Then, you know, inside and the outside, this cross multiplication. So x of C times this denominator, okay, let me see. Okay, let me move it over here. X of C plus, so x of C times this. Let me write it over here. This is equal to x of C divided by input W of C. So if I do this multiplication, inside and the out, or cross products of these. So I have x of n plus ak x n minus k is equal to b0 w of n. So I do this multiplication and take this inverse Z transform. Okay? This is ak. Is this clear? So x of z times 1 gives me inverse Laplace x of n. X of z times z to the power minus k gives x minus n minus k. Okay, I have this. Now, very good. So this is the recursion. Again, in this recursion, if you just look at this recursion, it's not clear how you run this recursion. This information is missing in the recursion. No surprises, because I have not used this information, causal information for the h of n, over here. This is an additional information. And by just processing this, inside out multiplication, I get this one, so this information is not used. So in addition from this, we say that this recursion is run in forward direction. Forward n, let's say. So what do I mean by this? If I have, for example, x of 1 million, then x of 1 million is equal to b0 times w of 1 million. Move this to the other side. 1 previous samples. So this is ak times x 1 million minus 1. Okay. So this is 1 to p. a2 times x 1 million minus 2, and so on. Okay. Then you get a new 1 millionth sample of x. Then you get 1 million plus 1 by running this recursion. So you are increasing n. Okay. Of course, you can do it in the other way around. That will be an anti-causal operation. So you are starting from positive values, let's say. You run this recursion, so you are decreasing the n at every step, and you are getting negative n's and up to negative minus infinity with these indices. Okay. So that is it. So let me write that recursion over here one more time. I have this. Now, what should I do? Well, this is always valid. So how about this? If I take this equation and multiply it by xn minus k conjugate, but let's make sure that I'm multiplying by a sample in the history. So this is a previous sample. Okay? Okay. If I multiply by that and take the expected value of both sides, what do I get? Is this clear? I am multiplying this relation, which is the input-output relationship of the filter, always valid. Then I multiply it by a previous sample after conjugation. K is greater than or equal to 0, or the same sample or the previous sample. Okay? Then I take the expectation. If I do that, what do I get? So this becomes product of these two, expected value. I have Rx of k. Am I right? Then this becomes, well, let me put a dummy variable over here, k prime. This becomes ak, expected value, x of n minus k, x of n minus k prime, am I right, is equal to, this is this multiplication, b0 w of n x n minus k conjugate over here. So I have such a thing. Now I know that filter output is, white sand stationary from our earlier information. Now I know this is equal to Rx This is the wrong one, sorry. N minus k prime. This is n minus k. So which one has conjugate? This one has conjugate. Okay. So this one is Rx k minus k prime. Okay. Is this okay? X n minus k. This is the conjugated one. And so on. Okay. So what do I see? If I write this, Rx of k is equal to k1 to p ak Rx k minus k prime so this is equal to expected value of W of n x conjugate n minus k. Okay, I get something like that. Interesting. So there is something like a recursion, a very similar recursion that we see. But on the right hand side, there is still some expectation that I need to calculate. So how can I, get that expectation calculation done? Now, how about this? Well, this is equal to right hand side b0 I have two issues right now. K is not equal to 0. Well, in this discussion, K is, let me write a brief note over here. Let me write it over here. K is greater than or equal to 0. Okay? This is our assumption over here. So when K is meaning that not 0, that means that K is a positive quantity. Okay? If K is a positive quantity, this is what? W of n. So this is my input to this filter, AR filter, which is a causal filter at the end time instant, okay, W of n. And when K is a positive quantity, this is the output at an earlier time. Okay? But this is white noise. And this is a causal filter, please remember. So output at an earlier time is nothing but a linear combination of the input samples up to that time because of the causality. So output at n minus k is equal to the linear combination of the input up to the samples with the index n minus k. Okay. So this is, you may say, a new incoming sample. Okay. So this one is independent from this one, because why do I say so? Because what we see is this. This is white noise sequence. This is the summation of white noise samples, and all of these samples are distinct from W of n. Okay? Meaning that once I calculate this product, I get 0 over here. Okay? Because they are white noise. So I get the white noise autocorrelation for all the legs except 0th leg. Okay? I get some, calculations, but only the leg with the 0 contributes to this summation. So that is it. How about this one? When k is equal to 0. So when k is equal to 0, what do I have? So let me write this part. K is equal to 0 case. Expected value of W of n x conjugate n minus k, and k is equal to 0. Okay? So what is this? This is equal to expected value of W of n. So this is x conjugate n. And x conjugate n is this, recursion. So this is this one, b0 W of n minus samples. Some samples in the history. Okay, there is a conjugate also over here. So again, what do we have? So this is white noise sample at that time. These are the same. And these ones, so this is the output of the filter at the earlier time. Since the filter is causal, the output is a function of, samples of the white noise. But those samples do not include W of n, because these are the samples in the history, because of the causality. So this W of n times those xn minus k, then it will be equal to 0. So what do I have it after expectation? I have this product. So this is W of n. This is equal to W of n magnitude square. Okay? Because I have a conjugate over here. This one is conjugated, this one is conjugated. I have this. Then this is equal to B0 conjugate RW0. Then this is equal to B0 conjugate sigma W0. So this is this one. So what do I have is over here B0 conjugate sigma W0 for this one. And our final result, now this is then equal to this calculation. This is equal to B0 magnitude square delta K. When K is equal to 0, I have B0 magnitude square sigma W square times delta K. When K is equal to 0, I have this. When K is non-zero, it's equal to 0, and so on. So let me so let me write this. Then Rx of K, recursion, plus I have K prime 1 to P AK Rx K minus K prime, okay, is equal to B0 magnitude square sigma W square delta K. But please remember that we have derived this with this assumption. K is greater than or equal to 0. Okay, so we will continue from this point on after a break.